a pair of images and we were using disparity and trying to estimate the overall depth of points in the scene at every pixel. We could view this as a geometry problem like the kind we've been dealing with this week and say, well, we want to infer the location of every point in this image, but maybe instead of having two cameras, maybe we have something like a single camera pointing at the scene and a projector pointing at the scene. So here you see the setup. There's a little camera pointing at the scene. There's a projector. So we have a setup that one of the previous MSc students built, very much like this. So we've got a camera and we've got a little pico projector, and they're pointing at the scene. Projectors, for our purposes, well, for most purposes, can be treated like cameras. Actually, we have light rays emanating from a camera center. They have intrinsic parameters in terms of how the light rays are going, and they have extrinsic parameters. So we can talk about calibrating projectors the same way we talk about calibrating cameras. What we're going to do in this setup is we're shining a known image. So we get to decide what comes out of the projector. We're shining a known image at the scene. Presumably there's no other light or not significant amounts of other ambient light in the room. And so the only light falling onto the scene is coming from our projector. And we're taking a picture with it. And our goal is to find the depth. Now, if we were doing this, let's say we're doing this the slow way, the hard way, we would very quickly run into, well, maybe you can figure out what the problem is. I tell you the intrinsic parameters of the camera and the intrinsic parameters of the projector. I tell you the extrinsic parameters of both of them. Now, to estimate the world coordinate of a point in this scene, what am I missing to be able to use the models we talked about this week?
Another camera.
Sorry?
Another camera.
You can say you're missing another camera because then you could use a different technique, but we're not allowed. I'm not allowed to give you another camera. I've given you lambda 1 and omega 1 and tau 1, for the 1 being the camera, and I've given you the same thing again for the projector, right? Big lambda, omega, and tau. And I want to know what is the depth of the top of that green cone right there. Yes?
You need some test data to compare it to, like training data.
Why do I need training data when someone has learned and given you all your intrinsic and your extrinsic matrices?
Well, then you still need to know like what the type. So that would mean you know everything about where the light is coming from.
I do.
Okay. Oh, then you don't need to do that.
Okay.
Do you need a point that you could say this point in space is in my camera and in my projector?
That's it.
These coordinates.
We need to know the x-coordinates of where does that point project. Where does this point on the top of the cone project in our image? So far, we've taken it as granted. We've always said, great, someone has handily told us that W1 corresponds to X1. And if I have more points in the world than W2, 3, 4, I also have, and I know they're corresponding X2, X3, X4. So there's this correspondence that we have. But in this case, this is the real problem. No one's handed you this correspondence. It's not like yesterday's assignment where someone has handed you a collection of points and said that are, let's say, in that panorama building part of the lab yesterday. No one said, oh, these points correspond to these points. We don't know that yet. So I could propose to you a very naive strategy where I'm going to project an image out of the projector where all of the pixels are off, and only one of them is on. That means that now we have a single ray. We know which ray is coming out of the projector, going into the scene. The scene, as viewed from the camera, should be mostly dark, right? Except for a single part of the scene which is going to be bright. So there's nothing wrong with that strategy, let's say. I hope we agree that that sort of solves the problem of correspondence now. We have a point in our image plane of our camera that's brighter than all the rest, and we say that corresponds to a point in our projector. And so we have two rays. They're hitting the scene someplace. Where those rays intersect, that must be the location of the world point. So now we just have to go through taking a bunch of pictures. Each time in the projector, we just illuminate a different pixel. Okay? This is a viable strategy, and essentially we're going to do that, only we're going to be slightly more clever about it. Everyone okay with this strategy, though? You understand we're trying to do our triangulation, our inference that we've talked about. That's problem number 3, but in a real-world scenario, and we're going to do so using a projector and a camera. We agree that we could have used 2 cameras and tried to figure out correspondence by doing searching and so on, but let's say that's not necessarily as reliable, especially when you have surfaces that don't have a lot of texture, right? As we've seen in previous examples. Right. So what's the clever way of doing this? What we're trying to do is maybe take advantage of the fact that our projector can project lots of rays of light at the same time. I mean, I'm sure you're thinking, wait a minute, well, I can do better than the 1 pixel at a time strategy. Maybe I'll turn on 3 pixels at a time. One will be red, one will be green, one will be blue, right? And then I'll just look for corresponding colors of pixel in the other image. This is an even more efficient strategy. So we're basically saying we want to do this search. We want to figure out what thing seen or illuminated by the projector corresponds to the pixels in the camera. And the way to do that, so what you should be kind of seeing is, if I look at this scene, lots of cones, right? Rows of cones in this oval-shaped mask. You should see here kind of vaguely the shape of a few different cones and an oval-shaped mask. All right. So what we're going to do is we're going to try to identify points, let's say that point right there. We're going to try to figure out which point is that with respect to what the projector is shining. Now here, the projector, instead of shining 1 pixel on and the rest off, which would have localized this immediately, it's shining a bunch of stripes, black and white stripes. So the stripes that it's projecting are actually not deformed like this. You see these sort of bumps and waves in the stripes. It's actually just perfectly horizontal zebra. So we have this challenge. This point here that I'm pointing to with my arrow, it happens to be bright right now. So we know that this point in the camera image number 1 corresponds to a white pixel in the projected image number 1. So we have 2 images, projected zebra and the actual image version of the scene, right? And I now know that at least that point that I was pointing to doesn't correspond to any of the pixels that are off in the zebra image right now. Fair enough? Is that enough to do the correspondence?
Try the higher resolution.
So the answer is no, and the suggestion is coming, well, what if you try a higher resolution? So we could increase the resolution, and so indeed we try a higher resolution, right? We still are going to be confused about whether that point that I was pointing to up there, it's still white now, right? So it still could get confused with any of the pixels that are white in the in the zebra image, right? So let's do this. The projector image looks like this. Right, and the camera image is going to have these wavy sort of shapes, right? So we still don't have the one-to-one correspondence. If we just do big zebra stripes or if we do narrow zebra stripes. But the cool thing is we can acquire multiple images over time, which means that we can sometimes be projecting for the same location in the zebra image. We can sometimes, for this given location, we can sometimes turn it on and sometimes turn it off and keep track of what we did, whether we turned that on or off. And then when you're imaging at a given location, right, maybe right there, we go monitoring, high or low. Now, of course, there'll be objects in the scene that are painted with different colors, so high and low is sort of more important here than whether it actually looks white or black. But we monitor what this is doing for each location, and we see if that matches any of the patterns that we created here. So that's what you're seeing here on the left. On the left, you're seeing kind of a cross-section of what the zebras are. So look at the first column of pixels. In the first column of pixels, our so-called zebra it's an image with the top half being white and the bottom half being black. Okay, so currently, any pixel that looked white in the camera image we just localize that it's in the top half of the scene, right? But now, the second column we have this pattern of a bit of white, black in the middle, and then white again. So now we can look at our given location in the image and say, well, hold on, your pattern in the first image was white, in the second image you were black. Okay, if you were black, that means you must be somewhere between here and here, right? And we keep each column as a new projected image until the last column here is this very dense, every row is a different color. So you end up with this binary pattern that says on, off, 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 on, off. That tells me, oh, well, the only row with that combination is this one here with this red line, right? I know where you are. I know that whatever this point here corresponds to this point here in the zebra. We now have two rays that we can calculate where they're intersecting because we've already learned all the intrinsics and the extrinsics of the problem, and we can calculate, because we're triangulating, we have its depth. So, a tricky, sneaky way of doing the correspondence problem. And every year at every vision conference, there are always new algorithms for how to design a better encoding pattern that will get you this localization in fewer images. Yes?
But we have to do this binary thing once for the horizontal and once for the vertical lines?
Indeed. Sorry, yes, I didn't even mention that. It's just illustrated here. So this will tell us where we are vertically, and then we have to do the same sort of, well, a similar type of pattern, a similar search to establish where we are horizontally. That's right. Yes?
Just a triangulation step. How does that work, please?
So our triangulation step is we see.
So basically, you have your image looking at it from the front, and then you map it to the one looking at it from a slightly lower angle. You can match the points one to one in those two images.
Yes. So each point we know is a ray, right? Because we have the camera information, so we know that it's a ray. Well, I think we have this. This was the reconstruction problem. Problem number 3, reconstruction. We have J cameras, in our case a camera with a ray coming out. We know which ray we're in because we've determined which pixel here corresponds to which pixel in the projector. Yeah? And in this case we're saying actually the point in question is sitting right there, and image in the camera, and it's sitting right there in the projector. Therefore, the ray that comes out of here and goes through x2 and goes out into the world intersects with the ray that goes out of the center through x1 should intersect right around here. There's the answer. Yep. And so we've done that for the kind of general case.
You do that for every single point.
And you do that for every
images, and then you have a.
Exactly. You now have an estimate of the world coordinate for every point independently of every other point. Yeah? Okay. So, one application. This is an example depth and structured light for that cone scene, where here one of the big problems is occlusion, actually. So if you have a projector over here and you have a camera over here, it's possible that the light won't go into the, well, let me go back to the color image so we can talk about this. You see the fence in the upper right? Yeah. So imagine if you shined a projector with light through the fence from one angle, and you took a picture from another angle, you would see the shadows, right? You'd see places where no matter what the image, whatever the zebra was, you wouldn't be getting any light because it's occluded. And therefore, at those locations, you don't have any correspondence. You tried to decode the pattern, the binary pattern, high, low, and it just didn't change. It was always the same. So you're left with no estimate of the depth. All right. So, has anyone seen Connect? Yeah. So if you look at the Connect image, so if you go online, people will show you what Connect is projecting. It's doing it in infrared, though. Instead of using a visible light projector, they're projecting infrared light. This is it. This is the algorithm. Except instead of using the binary code, they said, you know what, we'll project these funny shaped blobs. And from those funny shaped blobs and our known calibration, we can pretty accurately localize points because we know enough not to look for, let's say, a zebra point here all the way down here on the right. So they're saying basically the search is much more limited. You don't need so many patterns. You don't need such a sequence of different zebra patterns because really it's going to end up here. If it's if it's an object very close by, then the zebra shape will be quite deformed, but even then it's still going to be pretty localizable. And because of the occlusion problem that I mentioned, Connect has these shadows, right? These areas where it can't estimate the depth. And so, yeah, that's a problem if you're trying to do 3D scene reconstruction, and the people who do the pose estimation have to contend with that. All right. So, a different application of the work we've been doing is to move into multiple cameras, and we'll be doing more with multiple cameras next week. But imagine that you've got multiple cameras looking at a scene, and the big challenge is to reconstruct the full 3D shape of the object, not just its depth. I want to reconstruct that object so I can have a CAD file of it. Now, apart from the fact that the CAD file is a surface mesh, let's treat this as voxels, right? So 3D pixels. We're going to say, I want to figure out that roughly from this volume, which parts of the volume are occupied, so the voxels are on, and which voxels are off. I'm giving you cameras that are, for which we know the intrinsics, multiple, not just two, but many cameras. I'm giving you the intrinsics for them. I'm giving you the extrinsics for them. And critically, I'm also going to put a big blue screen on all sides around this thing so that the segmentation of chair versus not chair is very easy. Right, so I've given you a lot. All right. Now, with all of that, can you reconstruct the 3D shape? And the answer is mostly. Okay, so Oh. This is our object in the world, or think of that chair, our object in the world. We take our camera, my high-tech camera, I take a picture from here, right, and I know that that is a pixel that belongs to the chair, that ray, and the ray just above it is hitting background, so it's not chair. Chair, not chair, for every pixel I take in this image. And what you're seeing here is this top-down view, right? We're looking from above at the chair. I was standing over here. And we see that of my field of view, only the stuff in the middle was chair. The stuff off to the sides was not chair. So all of these voxels get carved away. We could think of it really as like a sculptor chopping away the excess marble on either side. That's all gone. And in 3D, not only is the stuff to the right and to the left gone, but also the stuff above and below is also gone. Currently, if you stop right there and ask me what is the shape of the object, I'm going to say, well, it's this gray-shaped wedge thing. That's what I know about it. Obviously, that's not quite right. So we take that same camera, move it around to another angle. So I might walk around, take another picture, and now the gray area where I say, oh, the object is sitting inside of here, this is my current reconstruction, gets smaller, right? More closely approximating the shape of the object. Increase to 3 and 4 and 10 cameras, and you should be seeing that where our gray shape is more and more closely approximating the true red shape of the object. Yes?
The bit where it's concave, how do you...
That's why we can't get the exact shape using this method. Because of the concavity here, you can never put the camera in a position that will capture that will see, this is not chair and this is chair. We happen to see it from above, which suggests that if you want a more accurate version of this, you'd better move the camera up above, and then you might be able to see it. But obviously the chair is chosen in such a way, right, specifically so we can see, well, you'll never get that scooped part where the person sits in the middle of the chair, because there's no place to put the camera that will see that.
There are no cameras which have sort of a structured light method built in?
Well, the Connect Fusion is one, and so people are using that, and Connect Fusion is this algorithm made by some of the same people that tries to do this, and it does a voxel-based reconstruction, and so that's kind of the newest method that uses structured light. The other method, which is also active lighting, is time of flight. So we have a time of flight camera. So it works a little bit like a radar gun, where you fire, in this case, light, and it comes back, and you see how the phase of the wavelength has changed, and you say, oh, based on that, it must have traveled, well, the time of flight. How long was that light traveling? So there are sort of hardware solutions, and the next Connect is probably going to be actually a time of flight method. But let's say that's more of a physics lesson, and it just so happens that for now, Connect is using a technology that's sort of easier to explain. Okay, that's shape reconstruction. I'm going to press on to the rest of chapter 15. Part of it this is kind of the motivation for chapter 15, but you've already seen some of this, right? In this case, an actor was filmed from 15 cameras, and then we say, okay, well, we know where each of those 15 cameras was, so now when someone takes a little piece of cardboard with a known pattern on it, and they estimate the homography of the pattern, as you were doing in part 2 of yesterday's lab, if you got that far, then you can sort of choose which cameras, images, to project, right, to show the user. So this way, you're sort of superimposing the character, and you can move your virtual camera around as long as you can see the pattern and estimate the homography, because then you know the rotation and translation, where to project this guy. Now, this is a combination of obviously segmenting the background object and doing the visual hull carving that we were just talking about with the chair, right? So that we can then paint the voxel there with his beard, and the voxel there with his hair color, right, and so on. And then when we view it from a different angle, it still looks a little bit like him. Obviously, the more accurate the 3D shape, right, the more accurate this is, the better the reprojection will look. Right. So let's jump to chapter 15. Now, you saw in the lab why we had to sort of jump ahead and do chapter 15 before we're quite done with chapter 14. The idea being that we had to introduce our different transforms so that we can talk about how to estimate their parameters. And we introduced 4 transforms, right? I'll remind you of the names, but hopefully you can name what degrees of freedom are available to each transform. So the first one was Euclidean. So given a projection of the world onto an image, what kind of transforms could the Euclidean transform do to the pixels on that image? What degrees of freedom are there? Rotation and translation. Okay, great. Then we had similarity. What degrees of freedom did that have?
Rotation, translation, and scaling.
Rotation, translation, and scaling. Indeed. Okay. What was the third one?
Affine.
It was affine, which introduced what extra degree of freedom? Skew, right. So that allowed us to do skew. So we had skew, rotation, translation, and scaling. And then finally we had homography, right? Also called the projective transform. Projective transform, most degrees of freedom, everything we've seen before, and in fact, it doesn't even need to keep parallel lines parallel anymore. Any 4 points map to any other 4 points. All right, so we're intimately familiar now with this setup where we said, okay, we can set up this constraint that we need our 2 rays to agree with each other. The ray that's pointing into the image plane and hitting the pixel in question, and the ray that's going out into the world and hitting the corresponding world point in question. When they're aligned, then the cross product is 0, and we know we've correctly brought into registration the planar object in the world and the plane of our image, of our camera image, right? So we said, all right, we actually, with this cross product, while we have what it looks like 3 equations, there's only 2 independent equations, right? So you know that if you have non-independent equations, then you're not actually constraining the solution anymore, right? So we can just eliminate the 3rd row. We can take the SVD, take the last column of V, and that is our homography. With our homography, we are essentially done. If all we want to do is explain how to map things from one plane to another plane, like a planar world object to the image plane of the camera. All right. We said we weren't entirely done with that because we will want to do a little bit more. Namely, we're going to want to estimate how did that plane translate and rotate in the real world with respect to the camera. So we'll do that next. If you did that in the lab yesterday, brilliant. I think I rushed through it a little bit in our sort of extra few minutes of lecture that we did in the lab. Just a reminder, when we have a homography, or any one of the transforms that we've talked about, that's telling us how to map a given point in the world onto the image plane. And we know that because these are both planar, right, the real world object and the projection onto the camera plane, we know that there's a one-to-one mapping. So when we want to do inference, i.e. we want to estimate, for this XY location in the image, where is that on the plane? What do we have to do with the homography? Almost. The homography goes from world to image coordinates. So if we want to go the other direction, we have to invert it. We just invert the homography and pre-multiply it by the xy coordinates. All right. So we said, here's our homography. We worked hard to solve for it, right? Because we had some training data, some corresponding pairs, and now someone comes along, and so we now have this method of turning world coordinates into image coordinates. But I've asked the question the other way around when we come to problem number 3, the inference problem. I've said, yeah, but I've got an xy point. I've got a point in the image, and I'm trying to figure out where is that on that plane. And the answer is, take that homography, invert it, and that'll tell you your UV coordinates in the world, but in a very planar world, right? That's the assumption with homographies. All right.
Now,
Yes.
question. So yesterday in the lab, we were projecting all the images from all the pixels from image 1 into the image 2.
Yes.
And using the homography, and then we inserted the value of the pixels in image 2, the homographies into the pixels in image 1 that were in the frame. So if we would do the other way around, we would project the homography, the pixels of image 2, using the inverted homography into the image 1.
Yes.
How would that work? Because it was multiple pixels from image 1 projected onto the same pixel in image 2. So you had more pictures from image 1 going to image 2. So image 2, would that deliver the same result, or?
So you wouldn't get this. So you can do a mapping from one image to the other, from one plane to another plane. That's the point with the homographies. You have two planes. It happens that we've been referring to one as the plane living in the world and the other one living inside of the camera. In your assignment in the lab, we were saying, well, okay, there are two planes, and one is an image and the other is an image. Okay, fine, but there are two planes. Your question is, well, what about this fact that you have, at a given location, you have two pixels? And if you took multiple photos of the same scene, you would have more and more versions of what should be happening at that location in the world. And so, indeed, when you have these types of panoramas, you have a choice, actually. You know the mapping both ways, right? 1 to 2 and 2 to 1, image 1 and 2. And you could now choose to say, well, at this rendered view, I'm going to use the version of that pixel from camera 1, or I'm going to use the version of that pixel from camera 2. But you can do a mapping from one or the other. What we did in the assignment is we said, or in the lab, if you recall this image, right? We said, actually, we'll make. Let me start from the middle. We have image 1 with stuff in it. It was image 1, wasn't it? And we're going to pretend that our canvas, our imaging plane, isn't narrow like this. We're going to pretend that it's actually quite big, just sort of undefined here for now. And we were mapping everything into this. There's no reason you couldn't do the same expansion of the field of view for image 2 and just do it the other way around then. Absolutely fine. But you still will have to choose which pixel do you want to use as the color for that location. And there are lots of research papers where they try to choose the color version that will be most compatible with its neighbors, so you don't see the seam of stitching, whatever the version of image 2 would be, right? So you don't see this jump. In fact, people use graph tests to choose between the multiple options of pixels that you have there. Okay. All right, so the part I rushed through yesterday was saying, all right, back to problem 1. You want to estimate the extrinsic parameters of your camera with respect to the world. And slightly inconveniently, someone's handed you a homography. You say, well, that's not what I wanted. I wanted omega and tau, this homography thing, is this matrix where everything is mashed together. In fact, really, everything is mashed together, right? So we have our rotation and translation is mashed together with the intrinsics of our camera. We never deciphered them yesterday, did we? Never told you what the intrinsics of the cameras were, camera 1 and camera 2. You didn't need them because, well, everything is mashed together inside of the homography. If, however, I'm asking you to solve problem 1 and I'm saying, tell me what is the rotation and what is the translation, then you're entitled to say, well, for problem 1, you've always given us big lambda, so give me big lambda. And if I give it to you, then you can say, ah, great, I can apply inverted big lambda in front of the homography that we have, right? And that gives us this new homography, this normalized homography in normalized coordinates. It's as if we had a camera with a focal length of 1 in both x and y and so on. So it's still a homography, it still does its job, but we've taken into account the knowledge that we had. Now, if no one hands you this kind of information, you will just proceed using the homography that you have and hope that, well, at least you can solve, let's say, okay, at least I can solve the problem for a normalized camera. But if someone gives you the camera, you know what to do. Fair enough? All right. Now, this homography, the transformed one, it still ought to decompose into a rotation and a translation with some scale factor, lambda prime. And this is what we were doing yesterday. We said, all right, this is a 3x3. I would really like to have actually a rotation matrix and a translation vector. So this is how we get our, this is how we could find our first 2 vectors of rotation, right? We take the first 2 columns of that, save the last 3 columns for later. We're going to need those for translation. We do the SVD decomposition, and use the U and V transpose to reconstruct what are the first 2 components, so the first 2 columns of our rotation matrix. And then we take this one cross this one, that will create the third one. And we say the determinant overall of the rotation matrix should be positive 1. If it's negative, then we just negate that last column and everything will be fine. Now the determinant will be positive 1 and we are essentially done with our rotation matrix. You now have a 3D rotation matrix and you can now rotate the bearded fellow, right, geometry to the right pose or the cube in the case of yesterday's lab, right? If you got to part 2, you can rotate a 3D cube so that it's oriented properly with the plane for which you computed the homography. You just haven't done the translation until you estimate that scaling parameter, right, which we mentioned. It's just taking the ratio of the phi's to the omegas, it's the average, and using that scaling parameter on the last column from your homography. That's your tau, that's your translation. You have translation and rotation. Yes?
Sorry, just a quick question, fairly basic. In the lab we had x and y and u and v were the coordinates of a point in the 2 images.
Yes.
In looking at a plane in the real world, x and y is from, well, either an image or, and then u and v, how does that relate to, I mean, it's a position on a plane, but I mean, how do we know what that is when we...
You might have to go measure it. Someone here has gone and measured how many centimeters is this point from the middle of the book cover.
Right.
And they've said, this point has some U, some V, and its W is 0 because it's planar, right?
So if we went and measured the side of a building and then took a photo of it, we could go, well, okay, but this is how the building is moved, or this is how we put a point at this place on the building.
Exactly. If you measured the points on the side of a building, and you took a picture of that, you can now estimate how much did your camera rotate and translate relative to that side of the building. And now you could do a special effect. You could superimpose graffiti right on that building, or you could do the opposite, superimpose, you know, what that building would look like without graffiti, and all you'd have to do is model a plane in OpenGL and transform it according to what we've just estimated to be our rotation matrix omega and our translation vector tau.
So it does require you to know some sort of previous information about the thing that you're looking at.
Oh yes, yes. So in special effects, when they go on set, there are people madly running around measuring the real world dimensions of things, or they do things like they'll forget to do that, and then they'll come back and they'll start looking up information like, okay, so how wide exactly is a stop sign? Because at some point we saw a stop sign, so we can try to use that because it's got a known size and so on. Or stripes on a zebra crossing and things like this. They've had to use, or because the actors are usually the same in each scene, they have used the height of the actors as ways of calibrating this. They go, all right, how high, how tall are they? And then they have to sort of ask gently because they need to know the actual height, not the sort of what Tom Cruise says he is. Okay. So, calibration, we're going to breeze through this because you've already basically seen this. Calibration, we have an unknown focal length. We don't know big lambda, but we have a world plane and we have a camera plane. And we said yesterday, well, what we'll do is alternate between fixing the big lambda and fixing the extrinsics. Let me just point this out. I've already given away the game. We're going to do this by looking at I different points, right? Because that way we can do a calibration. We have enough pairs of rows to make a big matrix. And we're also going to have multiple J's here. Now, we didn't see this before. The previous version where you saw problem 2 being sort of addressed by alternating between the two, we didn't really do that. We just said, oh, well, just make a 3D object, a calibration pattern that has sort of perpendicular walls and stuff. As long as you know the real world measurements, you'll be okay. Here what we're going to do is we're saying, but we're good at homographies now, right? We're good at planes, and that's what we can do. The problem with a single plane is it doesn't constrain your solution. You won't be able to estimate your calibration well enough from a single plane. So what we're going to do is we'll take J photos of the same plane. Now we have a different overall orientation of that same plane here 4 times. So we have J equals 4. But the intrinsics are staying the same. So yes, we have a slightly bigger problem to solve, but the more different versions of this board that we see, the more constraints we have overall for the intrinsic side of things. And this is the way it's normally done, and this is the way we do it in the first or second lab of computational photography, because it's very easy to manufacture a completely planar surface, and it's easy to get out the ruler and measure how wide are the squares, and it's important to measure how tall are the squares, because squares coming out of a printer aren't always square.
How does it know the rotation, though? I mean, this board looks the same.
This is a poor board. Sorry to cut you off. It's a bad board. I try to use boards where there is some identifying characteristic that tells you exactly which way is up. Here they're using the green bounding thing, and they're manually saying, okay, if the green is here, that corner is the same as that corner there.
And so the result is it just won't work if, say, you actually rotated the board more than 90 degrees without defining.
Indeed, but we're trying to be, this is a cooperative system. The user is not trying to trick the user taking the photos isn't trying to trick the user of the software.
It's more of the augmented reality when they're moving it around.
Indeed.
You need,
if you notice the patterns that were used on the augmented reality, they were quite square and symmetrical, except they would always have one of the off-diagonal squares, something identifying it as having a unique orientation. Yep, it's an excellent question. All right, so we're going to zoom through reconstruction. We already figured out that, all right, if I tell you it's a planar scene, I give you the information for the extrinsics of this plane, and I give you the intrinsics of the camera, you can mash them together, right? Multiply them out. That gives us a homography. We just call that T because I didn't want to get it confused with the homography that we estimated, right? A transformation T. And if we want to go from image coordinates, homogeneous image coordinates, we just apply the inverse of t, and that gives us our homogeneous world coordinates. Now, these homogeneous world coordinates are in the frame of the object of the world, right? If you wanted to know, well, hold on, I'm trying to project 3D stuff and graphics into my camera, you might still have to take that world coordinate, go into Cartesian, and apply the transform so that now W prime is in the point of reference of the camera. So it's a 3D coordinate expressed in the 3D frame of the camera, right? So in other words, we can now say, oh, it's this much x, this much y, and at this depth in front of the camera. All right, so that's the most typical use of our estimated W. Similarly, a robot needs to know where the object is with respect to itself. It doesn't help that it knows, oh yes, I found the lower right-hand corner of the book, right? It needs to know how far away is that lower right-hand corner so I can grasp it. All right, properties of the homography. These are quite cool, and for better or worse, you're already aware of some of these properties. I have a planar scene. Let's pretend. Yesterday, your planar scene wasn't so planar. It was the bay from somebody's holiday photos. If we take a planar scene, project it into a camera, there is a homography, we call it T1, relating points in the world to points in camera 1. Similarly, we could take a photo of this same planar scene with camera 2, and there is a homography T2 relating those. Because everything here is planar, we could also make a homography that just goes directly from camera 1 to camera 2. And that's what you were doing yesterday in the lab. So you're no longer surprised by this, but if someone came along and only gave you T1 and only gave you, so they gave you T1 and they gave you T2, and they said, now please explain to me where things from camera 1 should map to in camera 2, you'd be able to do that because you just have to undo one of the transformations and apply the other transformation. So in this case, T3, right, to decode which is which, we're going to apply T3. I'm very quick about this. I just want to make sure this is clear. I'm going to apply T3 to some coordinates. We'll call them A. And this is going to produce this is going to produce some coordinates B. Now, my question to you is, if T3 is written the way it is here, T2 times T1 inverted, which camera coordinates go in A and which camera coordinates go in B? Your choices are camera 1 and camera 2.
Camera 1 goes in A.
That's right. So camera 1 coordinates go in A. So when we pre-multiply by T1 inverse, we'll find the mapping that takes us from camera 1's coordinates onto the plane. And then that's pre-multiplied by T2, which projects from the plane onto camera 2. So this is camera 2, this is camera 1. Yeah? The arrow is giving it away here, but just look at these transforms and remember the T1 was the homography from plane to camera 1, and so if we're applying the inverse, that means we're undoing it. Yes?
So does this mean, is this why that if you have a binocular camera system, you don't actually need to go out and measure the thing? Because you know what T3 is, so you can work out what T2 and T1 are.
I wouldn't go that far. You know up to a scale factor what the world is. But yes, if you know the transformation between the two cameras, you're now able to at least able to say what is T3. You may not know what the orientation of the world is, but if you know the orientation of the world with respect to just one of the cameras, you've got it with respect to both of the cameras. That's right. So you only need to solve for 1 omega and 1 tau in that case. All right. Now, kind of weird, and this is why I want to desperately show this, and this will also appear again in computational photography. We've been talking about a planar world, but imagine that you have a non-planar world. It's quite a complicated world, actually, right? And the light coming off of this object with lots of depth to it, right, from this perspective, the light, you can imagine it coming along these rays that pass through an image plane and end up at the optical center. Now, I could have the image plane here. I could have the image plane in various other configurations, right? Usually you just change the focal length, so it's just moving the plane forward and backwards. But we could tilt it, we could do crazy stuff with it. And all of these images are related to each other by homographies, right? Because this is a plane and this is a plane, we can talk about where do these points map to in this image. A homography is enough to explain the relationship between all of these planes. Another interesting phenomenon is that if you have a 3D world and you've got these rays, so these are frequently referred to as bundles, right? This is a point in the world and it's projecting onto our image. We had our camera here where the dotted line was, and now we move our camera, but we don't translate it, we only rotate it. This is a very special case. If you only rotate the camera, so now the image plane is where the green thing is, well, just like in the last slide, there is a linear relationship called the homography that relates pixels from this image to pixels in this image. And the great thing about that is, it doesn't matter how complex this world is, right? You could keep doing that and make relationships that are based on homographies. This is why, when you go out to shoot a panorama, they say, try just to rotate the camera, try just to spin. If you spin, then it doesn't matter that there are buildings behind other buildings with lots of occlusions and so on. From the perspective of this O, if you can really spin around that O, all the bundles of light coming in are all going to be related to each other with homographies. So you can relate camera 1 to camera 2 to camera 3 and do the kind of stitching you did yesterday without any artifacts. The problem is that the O isn't always identifiable. It's not always sort of the middle of the physical camera housing, right? It's typically offset a little bit, and so that's not sometimes tricky to find. All right. We don't have time for Ransack, so we will pick it up on Tuesday. Thank you very much.